Hello students, welcome again to Chemistry 101, and we are going to continue with the chapter 4 today with precipitation reactions. And I just want you to please do these examples at home and try to write the net ion equations. But I want to show you how to solve number B here, the zinc sulfate and the magnesium chloride case, because this is a special case. Here's the question, zinc sulfate and magnesium chloride. The first step here is to predict what products can be formed. I'm assuming that the zinc will take the chloride, forming ZnCl2, and then the magnesium will take the sulfate, so magnesium sulfate. Okay, the equation is balanced. Before you carry on, you need to think what if zinc chloride will be aqueous or solid. All chlorides are soluble except there are some exceptions, but zinc is not of them, so this should be aqueous. Also sulfates, they are insoluble except of group 2, so that's aqueous. Okay, as you see, everything is aqueous and there's actually no solid forming, so this is called the molecular equation. If you want to start breaking this to ions, that will form Zn2 plus aqueous, SO4 2 minus aqueous. I'm just not going to write the aqueous here to save time, and this will be 2Cl minus aqueous. And ZnCl2 is also going to ionize because it's soluble in water, so that will give you Zn2 plus. And as you are predicting here, everything is soluble. That means everything is actually spectator ions, so Mg2 plus SO4 2 minus. So you see here everything is cancels out with everything else left and right. So all of these are spectator ions, and therefore everything cancels out. And actually, if you want to ask me what is the net ion equations, there will be no net ionic equation in this case. Okay, no net ionic equation. So that's about it for precipitation reactions. Please have your time to solve these two other examples, A and C, and also all the questions in the book. Now we're going to move to acids and bases. As you know from school, there are general properties of acids. They have sour taste, like lemon juice, it has a sour taste. They change colors in plant dyes, like litmus paper. Acids, they change the litmus paper into red. And they also, acids, they are famous to react with metals. So when I say metals, I'm not also only specifying gold and iron, but all the metals to the left of the periodic table, group 1, 2, and all the transition metals are considered metals. So acids, they react with metals to form hydrogen gas. An example would be magnesium will react with the HCl to form MgCl2 plus hydrogen gas. And you can also watch the video on YouTube on this reaction with sodium with water, where water is behaving as an acid in this case. It's a very vigorous reaction because of the fact that H2 is flammable, and with the heat that is formed with the reaction, H2 will go on fire. There's also a choice that acids will react with carbonates and bicarbonates to produce CO2. So 2HCl plus calcium carbonate will form CaCl2 plus CO2 gas plus H2O, and you know the famous reaction between bicarbonate and vinegar. Probably you've done this in school or at your home. This produces CO2. Okay. Also acids or strong acids, they conduct electricity, and you know why? Because they are strong electrolytes, as we mentioned in our previous lectures. Speaking about bases, they have a bitter taste, okay, and they feel slippery, and that's why soaps, because they contain excess base on them, they feel slippery. They change colors in plant dyes like litmus paper from red to blue, and also they conduct electricity. An example of bases are sodium hydroxide, and also the ammonia is a base. When we talk about acids and bases, we have three theories. There are three people who spoke about acids and bases. The first one was Arrhenius. Arrhenius provided a definition of acids and bases, but Arrhenius' definition was not that successful. Then Bronsted came in, Bronsted and Lowry, they came up with another definition. And then there is Lewis. In this chapter, we're going to talk only about Arrhenius and Bronsted. Now, Well, let's take a case where HCl gas, this is called hydrogen chloride, is added to a solution of, is added to water. What happens here is that HCl will dissolve in water. So we refer this to H2O liquid. And that is a one-way reaction because HCl is a strong acid forming H3O plus ions, aqueous, plus the Cl minus aqueous. What's happening here is that the HCl will donate an H plus to water, okay? And that's why it's called an acid. And that's Arrhenius definition for acid. Because water is taking the H plus, actually it's behaving as a base here, okay? So an H plus is called a proton because basically H atom contains only one electron and one proton. When you take that electron out, what is left is a proton. That's why H plus is called a proton. You can do this with ammonia. When you add ammonia to water, ammonia is a weak base. So the reaction would be NH3 gas plus H2 liquid. And because it's a weak base, the reaction will go reversible. It's 2 arrows instead of 1 arrow. But ammonia is a base. So in this case, the water will donate the H plus to that, forming NH4 plus. It's called ammonium ion, aqueous. Plus OH minus aqueous. Okay, so basically what Arrhenius said, that a base is something that gives OH minus, and an acid is something that gives H plus or hydronium ion. So this is Arrhenius definition, okay? So according to Arrhenius, acids are substances that ionize in water to produce H plus or hydronium ions, just in the case of HCl, and bases are substances that ionize in water to produce OH minus ions. Arrhenius has a little problem in his definition with the reaction that is going in the gas phase. Take an example, HCl gas reacting with NH3 gas. That should give you NH4OH, or sorry, NH4Cl. And so NH4Cl wouldn't be in the gas phase, it would be solid. And if you are not considering any water here, so there is no water involved, okay? This is not aqueous solution, this is a reaction that's happening in the gas phase. You see here that HCl is actually donating the H plus to the ammonia, right? To make NH4Cl. So this is where this agrees with Arrhenius. But there is no OH minus here. In this reaction, there is no OH minus. That's why Arrhenius fails in explaining these reactions. That's why Bronsted came in and they said an acid is a proton donor, but a base is actually a proton acceptor. So this is how he solved the problem or the dilemma of Arrhenius definition. So according to Bronsted now, a Bronsted acid is a proton donor, okay? And the Bronsted base is a proton acceptor. And if you apply the Bronsted definition to the ammonia case, ammonia reaction with water, in this case, water is donating the H plus, and that's why it's an acid. And ammonia is taking the H plus, or accepting the H plus, that's why it's a base. Now let us go back and take a look again at this equation, and I'm going to define here something called the conjugate acid and conjugate base. Now in the reaction with HCl with water, we agreed that this is your acid, because it's the one that is giving the H plus. And this is your base, water in this case is called a base. Now HCl is giving H plus to water, leaving Cl minus, and that's why this is called the conjugate. And water is taking H plus to form H3O plus, and this is called conjugate base, conjugate acid, sorry. Okay? So for each acid there is a base, and there is for each base there is an acid. Let me re-explain this concept again here with the reaction with ammonia with water. Now we agreed that in this case water is actually giving the H plus, and that's why it's an acid. And you saw in the HCl case it was a base, but now it's an acid, and this is called amphoteric species. And H3 is the base here. So NH3 is taking H plus from water to form this hydronium, to form this ammonium ion. So NH3 is a base, that's why it's called the conjugate acid. conjugate means conj, and H2O is giving H plus, leaving OH minus, and that's why it's a base, and that's why OH minus is the conjugate base. So you see, base, acid, acid, base. There's always a conjugate acid for each base and a conjugate base for each acid. I just want to tell you also one piece of information, that if you have a weak base, the conjugate acid will be strong, okay? And further, if you have, let's say here, if you go back to the HCl case, HCl is a strong acid, and that's why the Cl minus is a weak base, okay? And so on. So that's the idea of conjugate acids and bases. Now moving on to acids. Acids could be monoprotic, like HCl, HNO3, acetic acid. They are all monoprotic, and that means they have only one H plus, one proton to donate. Diprotic acids, an example would be H2SO4. Well, H2SO4 contains two protons. It gives the first proton in a strong manner. So the first step is one way. H2SO4 will give the proton and the HCl04 minus. And then the HSO4 minus has a potential to give another H plus, to give H plus plus sulfate ions. But the second step is weak, because HSO4 is a weak acid, and that's why we write the reaction in a double arrow here, or reversible arrows. Triprotic acids, they have three hydrogens, just like phosphoric acid, H3PO4. It gives H plus, and then to produce H2PO4 minus. This species produces H plus again to produce HPO4 minus, the hydrogen phosphate. The hydrogen phosphate is still having a potential to produce H plus plus the phosphate ion. Okay, so this is called a triprotic acid. Again, as I said last time, you need to memorize the 6 acids. Okay, the 6 strong acids, they are HCl, HBr, HI, and then is HNO3, H2SO4, and HClO4. Some people, they add HClO3 to the chloric acid, but for now I want you only to remember these 6. Everything else basically is weak acid. HF, HNO2, H2SO3, sulfurous, H2S, phosphoric acid, H3PO4, acetic acid. Those are all weak acids. Now this question tells you to classify each of the following species in aqueous solutions as Bronsted acid or base. So let me show you how to do that. We have HBr. So the best thing to do here is you react the species that you want with water and to see what's happening, okay? You know HBr is a strong acid, and it can give H plus to this to form H3O plus aqueous plus Br minus aqueous. So this is an acid, okay? The other way it's impossible, because how could HBr take an H plus? It becomes H2Br, and that's not possible. So this is your acid. Water in this case is the base, and here is your conjugate base for the acid, okay? So that's easy. The other scenario is you have NO2 minus. Now NO2 minus, if you want to know if this is an acid or base, you can just react this with water. Well, NO2 minus has no hydrogens to donate, so the best thing is it can take an H plus from water to form HNO2. You know HNO2 is an acid, right? That's why this is the base of it, because it's taken H plus, it is a base. And what is left from this is the OH minus. So NO2 minus is a base for 2 reasons. The first reason is that it is an H plus acceptor. It's a donor, it's a proton acceptor from water. And it also produces OH minus in solutions. So according to Arrhenius, this is a base. But no, we are not talking about Arrhenius here. The question is talking about Bronsted. So it is a base because it's accepting H plus. In 90% of the cases, a minus would indicate a base. But that's not always the case, okay? But in 90% in the cases. The third one is HCO3 minus. HCO3 minus, it's an ion, okay? So it might be a base. If you think about it, it can react with water. So it's gonna take an H plus, sorry, these arrows should be double arrow for these two cases, because HNO2 and this case is a weak one. So this one is also a double arrow. In this case, HCO3, if it's going to take an H+, it's going to form H2CO3, which is a carbonic acid. We know this is a weak acid, or just let's say acid here. Because this is taking H+, so it is a base. Okay, and what is left from water is OH- again. But the matter of the fact is that HCO3 minus, the bicarbonate, can also give H+ to water because it has H+. So HCO3 minus plus water, that H can go here to form the CO3 minus plus H3O. So this is an acid in this case. So you see here that this species, the bicarbonate or hydrogen carbonate, it behaves as an acid and a base. So sometimes an acid, sometimes an. So this is called amphoteric species. Okay, and water is a big example of amphoteric species. Amphoteric means changing; it changes. Okay, we say sometimes amphoteric person, that somebody who changes his mind all the time. So amphoteric species, like HCO3, is sometimes an acid, sometimes a base. Water is a big example of an amphoteric species. In the previous slide, we talked about H2SO4. Now H2SO4, in the first step, it produces H+ and HSO4 minus. So the H2SO4 is the acid. The HSO4 minus is a base. But in the second reaction, it behaves like an acid because it gives H+. So in this case, the HSO4 minus is the amphoteric species. Now I want you, please, to take a look at these three equations for phosphoric acid, H3PO4, and determine or identify the amphoteric species in these three reactions. Okay? You might need to discuss this with your friends. Now we're going to move on to something called acid-base neutralizations. As you learned before, acid and base always forms salt and water. Okay? This salt might be soluble or not insoluble in water, but for the case of the famous reaction between HCl and NaOH, when these two species react, HCl is completely soluble in water, so H plus Cl minus. NaOH is completely also soluble, so Na plus OH minus. That will give you Na plus Cl minus plus H2O. So the net ion equation for that is H plus OH minus gives H2O. But that's not always the case. If you have a weak acid, like HCN is hydrogen cyanide, or hydrocyanic acid if it's aqueous. If this reacts with NaOH, that will give you NaCN plus water. This arrow should be actually double arrow. It should be reversible. But HCN is not completely soluble in water, and that's why when you want to do this, you want to move it down as is. It does not form H plus Cn minus ions because it's not completely soluble. That's why we like to have it as HCN. NaOH is completely soluble, so we break it down to Na plus OH minus. The NaCN is also soluble, so that will give you Na plus Cn minus. And the water, usually we move it down as is, so water liquid. In this case, the only spectator ions are the sodium ions, the Na plus. And therefore, the net ion equation is that HCN plus OH minus gives Cn minus plus H2. Okay? That's the case of weak acid. We are going to do this example in the class, inshallah. And then we will also show you some of the reactions that forms gas formations. So that's about it for this section, the acids and bases. Next time we will continue with oxidation reductions, but the first exam is up to here, okay? Is up to slide number 42. That's for the first midterm. So thank you so much for listening and have a good day.